Now, if we will consider the problem of the day, we want to discuss going beyond the physics that we have had so far to try to find some of those new bits of modern physics which carry us very far indeed from the style of classical times. But I want to do this with the aid, let me say, of one device, as though I were taking a ship. It is, of course, not a ship, but it is one single kind of device which occurs in the world many, many times, over and over again, in all sorts of connections, with all sorts of shapes and sizes and purposes. And by looking at this one device, I think I can show what the physicist has found in his voyages well beyond the map. Now, you may recognize what these objects are. You see a spring with a weight on it, another spring with a weight, a piece of elastic band with a weight, a pendulum, a couple of other springs. I'm going to call them all by the rather ugly but still nice technical term, oscillator. All of these are oscillators. And of course there are many more kinds of oscillators in the world, and we will show you some of them and talk a little bit about how they work. The oscillator comes in many forms, and physicists can recognize in nearly all of them certain common properties, certain qualities in common. Let me talk a little bit about a few of them, and you will see what I mean. And of course, those of you who've studied some physics will be quite familiar with this account. Let me look first at the pendulum. Now, if you look at any of the other oscillators here, except the two pendulums, you will see really two essential parts: an elastic band or a spring, and the mass or weight that is on the end of it. Here the supporting string, while an essential part, does not change at all. I can't stretch it at all under this load. It's just a stiff string. It doesn't change its length. There is nothing springy about the pendulum. And yet, when I let the pendulum go, it comes back. What is the spring that is pulling the pendulum bob back to the center? Anybody? Go ahead.
Inertia.
That's interesting. Inertia, I think, would make it keep on going. Why would it go back to the center? If it started out this way, inertia would alone keep it going the same way, would it not?
Gravity.
Gravity. And gravity is the pull of what? It's not a word that makes it go up and down. It's a thing. What is that thing? Yes?
Pull of the earth.
It is the earth. The earth is the missing spring, just as you say, gravity we call it. But I'd like you to think of it as a physical thing. It's part of the pendulum. Without the earth, the pendulum would not work very well. On the moon, the pendulum worked quite differently from what it does on earth. So gravity, provided by the earth, provides the spring, the second part of the pendulum. I'd like to show you one more difference between the pendulum and the other oscillators, and I think this difference is easy to see. Notice this oscillator going up there in a kind of ragtime rhythm, rather fast. Let me put another mass on it, loading it down more heavily. Of course, it stretches to accommodate the mass, but then it will oscillate again anew about a new position, no change. But notice, what would you say about the rhythm? Slower, isn't it? More stately, perhaps waltz time now. And I could keep on going. But if I try this pendulum, you see its rhythm, and this one matches it pretty well. And if I put a heavy load on this, much heavier than the one that is there already, I don't think it will very much change the rhythm. Let's try it. Maybe do a little because it's hanging a little farther down than the main ball, but it's pretty close, yes? Yet I loaded it with a much heavier bob than was on there to begin with. So the pendulum somehow doesn't show the effects of putting more mass on, and indeed we can check that very carefully, and it does not. How can that be? After all, putting more mass on must have more inertia, must be harder to move. But what about the spring that moves it, which is the pull of the earth? What happens when we put more mass on? The spring pulls harder, yes? The earth pulls more, and the two go in perfect step, and therefore the time to go to and fro, which we will call the period, because the motion is periodic. One trip, is exactly like the next trip and exactly like the next trip with very small differences. So we'll call the period of the pendulum that time it takes to go back and forth. And the period of these gravitational ones where the spring is missing and is invisible, so to speak, or is all around us, beneath us, does not depend on the mass, whereas here the period definitely depends on the mass of the pendulum. Let us look a little farther at a couple of other examples which may be interesting.